Due to COVID disrupting students' education for the 2022 summer GCSE exams, the exam boards have released an advanced notice article that gives an insight into what will be on the exams this year. I'm sure your teachers have shown you this article already. In this version of the advanced notice article, I'm going to show you anything in green is definitely going to be on the exam. Anything in yellow may be on the exam in a small way, and anything in red will not be on the exam. In this video, I'll go over the green and yellow areas to help you prepare for the Combined Physics Higher Paper 2 exam. Here's SP8, Energy, Forces Doing Work. You're supposed to be able to describe the changes involved in the way energy is stored when systems change. So what that means, when a system changes, that could be a car braking, which would be kinetic energy stored in the car getting turned into heat energy stored in the brakes. It could be a light bulb, where there'll be electrical energy getting turned into light and heat energy. Draw and interpret diagrams to represent energy transfers. So an energy transfer diagram, for example, for a bulb would be electrical energy going in and it's getting converted into light, useful energy, and heat, which is wasted energy. Explain that where there are energy transfers in a closed system, there is no net change to the total energy in that system. What that basically means is what goes in must come out. So it's the law of conservation of energy. For example, if 200 joules of electrical energy goes in, 200 joules needs to come out. Now, not all of the energy that comes out will be useful. There's only 80 joules here that's actually useful. 120 joules is being wasted. But it's still there. 200 went in and 200 came out. You just can't use this wasted energy for any further useful energy transfers. Identify the different ways that the energy of a system can be changed through work done by forces, which basically means mechanical work. And that's when a force moves an object through a distance. Using this equation, work done equals force times by distance. Electrical equipment. So electrical work, for example, could be charges moving due to a potential difference or voltage. And heating, well, that would be something like heat energy transferring from one place or object to another due to a temperature difference, which can be caused either electrically, but from current, or by chemical reaction, for example, burning a fuel. Describe how to measure the work done by a force and understand that energy transferred in joules is equal to work done. There we go. Energy transferred is equal to work done. Now remember, work done is force times by distance if you're talking about it in a mechanical sense. In other words, when you're moving things. Recall and use the equation work done equals force times by distance. So there it is there, W equals F times by D. But you could also see it as E equals F times by D, because remember, work done equals energy transferred. So it's just a case of you putting the numbers in. Describe and calculate the changes in energy involved when a system is changed by work done by forces. So in other words, it's just energy transferred equals force times by distance. So they'll just give you the numbers, you've just got to pop them into your calculator. Recall and use the equation to calculate the change in gravitational potential energy. So again, it's just this equation, and you've just got to pop the numbers in. So the change in gravitational potential energy equals mass times by gravity times by change in height. Recall and use the equation to calculate the amount of energy associated with a moving object. In other words, you've got to be able to calculate kinetic energy using this equation. Kinetic energy equals a half times by the mass times by the velocity squared. Make sure you square the velocity first before you do anything else. Explain using examples how in all system changes energy is dissipated so that it is stored in less useful ways. In other words, you always lose energy as heat and sound, and it goes to the surroundings. And that's usually because of friction. Explain that mechanical processes become wasteful when they cause a rise in temperature, so dissipating energy in heating the surroundings. Well, that's what I've just said there. Mechanical processes, in other words, it's friction. When objects move and rub, it causes heat and sound, which dissipates to the surroundings. Try to memorise that statement there. It could be worth up to 3 marks. Define power as the rate at which energy is transferred and use examples to explain this definition. For example, that ties straight in with this equation. The power equals energy transferred over time. Power is measured in watts and energy is measured in joules and time is measured in seconds. So 1 watt is equal to 1 joule per second. And there we go there. Recall that 1 watt is equal to 1 joule per second. And recall and use the equation for efficiency. So efficiency equals useful energy transferred by the device divided by the total energy supplied to the device. For example, a bulb. If we put 200 joules of electrical energy in and 80 joules gets turned into useful light and we've wasted 120 joules, to get the efficiency you do the useful energy that came out divided by the total energy that you had to put in. So in other words, 80 joules of light energy came out, we had to put 200 joules in, 80 over 200 comes out as 0.4. Now if the examiner wanted you to express it as a percentage, multiply that by 100 and it comes out as 40% in this case. Unit SP9, forces and their effects. There's only one thing that we need to learn here, and that's 9.10. Explain ways of reducing unwanted energy transfer through lubrication. So what they're talking about here is when you've got moving objects, you're going to have friction because the objects are rubbing against each other. So if you lubricate the surface, you'll create a little bit of space where the objects can move over each other easier. Now, how do you tell the examiner that? You say, apply oil to the moving objects. For example, a gearbox or a bike chain are moving objects. That'll reduce friction, which reduces heat and sound from being produced, which is wasted energy. Because you often get friction in motors and things like that, and you don't want the motor getting hot. SP10, electricity and circuits. 10.1. Describe the structure of the atom limited to the position, mass and charge of protons, neutrons and electrons. In other words, you've got to know where each of these particles are in the atom, what their mass is and what their charge is. So the proton is found in the nucleus. It's got a mass of 1 and a charge of +1. The neutron is also found in the nucleus. It's got a mass of 1 and a charge of 0. Neutron is neutral. Proton was positive. And the electron is found in shells that orbit the nucleus. Its mass is approximately 2,000 times lighter than the proton and the neutron. It's 1 over 1,835 if you want to be precise. And the charge is -1. 10.2. Draw and use electric circuit diagrams representing them with the conventions of positive and negative terminals and the symbols that represent all of these things over here. So the cell, the positive side of the cell is the large side. What I tell my students is if you add something, it gets bigger. So the big side is the positive side and the smaller side is the negative side. And that goes for the battery as well. So we're only interested in the outermost part of the battery there and then the outermost part of the battery there. So that was big, so that's the positive side of the battery, and that was small, so that's the negative side. Closed switch, Harry Potter's glasses. I've got a nice video that goes over all of these. Voltmeter is a circle with a V, it measures voltage. Ammeter is a circle with an A, it measures current. Open switch is Harry Potter's broken glasses. Resistor is just a box. Variable resistor is just a box with an arrow through. I like to think of the arrow there as like an upside down V, V for variable. A lamp can be represented either as an X-Man badge or as an omega sign inside the circle. The motor is a circle with an M. Diode is D, I, O, first three letters of diode. A thermistor is a resistor with a thermometer through it, or it looks like a golf club. An LDR is a light dependent resistor, so that's a resistor in a big circle to keep it dry because it goes on top of lampposts. And here's the sun shining down on it. And an LED is a light emitting diode, so it's a diode D-I-O that gives off light. 10.3. Describe the differences between series and parallel circuits. A series circuit has only one loop. A parallel circuit has more than one loop. Recall that a voltmeter is connected in parallel with a component to measure the potential difference of voltage in volts across it. So there you go, we're trying to measure the voltage of that bulb. So you put your voltmeter in parallel across the bulb. 10.5. Explain that potential difference. Voltage is the energy transferred per unit charge passed, and hence that the volt is a joule per coulomb. So in other words, it's basically this equation here. Voltage equals energy over charge, which is down here. So, but rearranged, E equals Q times by V. So energy, EastEnders, is the Queen Vic. Energy, charge, voltage. You're very often asked for an alternative unit for a volt, so make sure you memorize 1 volt is the same as 1 joule per coulomb. 1 volt is 1 joule per coulomb. Recall that an ammeter is connected in series with a component to measure the current in amps. So here we go, there's the ammeter in series, so one thing after another. Doesn't matter if the ammeter is before or after the other component. 10.8. Explain that an electric current as the rate of flow of charge, and the current in metals is a flow of electrons. So current is how much charge you've got divided by time. In other words, it's the rate of flow of charge. 10.9. Recall and use the equation charge equals current times by time. The way I like to remember that is when you're charging your mobile phone, you need to put a current into your battery, so that's why you plug it into the wall and you leave it plugged in for a certain amount of time. The more time you leave it plugged in for, and as long as there's a big current going in, then your mobile phone will get charged. And 10.10, describe that when a closed circuit includes a source of potential difference, there will be a current in the circuit. So a closed circuit just means a complete loop, and what we're basically saying is it's at the potential difference of voltage that creates or causes the current. So if you've got no voltage, you won't get any current. So what came first, the chicken or the egg? We're not sure, but what comes first, the voltage or the current? It's the voltage. 10.11. Recall that current is conserved at a junction in a circuit. That's Kirchhoff's law, which basically says current into a junction equals current out of a junction. They'll often ask you, if 4 amps goes into a junction and 2 amps comes across here, how much is coming down there? So it's obviously 2, because what goes in to a junction must come out. And same over here. 2 amps and 2 amps are joining back together and 4 amps are coming out. 10.12. Explain how changing the resistance in a circuit changes the current and how this can be achieved using a variable resistor. So we basically use resistors to control the size of the current. So if you've got a variable resistor, it means that you can adjust the resistance and that'll adjust the current. So if you make this resistance bigger, it'll make the current in the circuit smaller, or if you make this resistance smaller, it'll make the current bigger. I like to think of a resistor as being like a brick wall. The bigger the brick wall, the harder it is to climb over it, so the slower you would go if it was like an assault course. 10.13. Recall and use the equation potential difference equals current times by resistance. This is Ohm's law. V equals I times by R. Voltage equals current times by resistance. So they'll just give you some numbers and they'll ask you to calculate something. You might have to rearrange it. 10.14. Explain why, if two resistors are in series, the net resistance is increased, whereas with two in parallel, the net resistance is decreased. So in series means one thing after another. So in series there's only one route, so the current has to go through this resistor and this resistor. So that would be the equivalent of going through a 10 ohm resistor, because there's only one path to travel down. Whereas resistors in parallel, there's two paths or more to travel down. So that gives the current the opportunity to take one of two paths. So it doesn't have to go through both resistors, it goes through one or the other. The way I like to think about it is if you've got a football stadium and there's two turnstiles to get into the stadium, two gates to get into the stadium, then you can have people going in twice as fast. And mathematically, if the current gets bigger for the same amount of voltage, then that makes the resistance get smaller. So the resistance is decreased when you've got resistors in parallel. You don't actually have to calculate the resistance in parallel anymore. That's A-level physics now. 10.15. Calculate the currents, potential differences. So remember that's just voltage and resistances in series circuits. So they might ask you to work out the current, in which case do voltage over resistance. If they ask you to work out the voltage, do the current times by the resistance. And if you've got to work out the resistance, just do voltage divided by current. And they will, of course, give you most of the numbers. And you've got to work out the final number. 10.16. Explain the design and construction of series circuits for testing and measuring. So this is your standard test circuit. You've got some kind of power source such as a battery. There's your component under the test. You need some way of getting the current. So get an ammeter in series and put a voltmeter in parallel. And then in order to get the resistance of that component, just do the voltage divided by the current. And if you've got to get multiple readings so you can create a graph or something, then you put a variable resistor in as well. So you take your current and your voltage reading, and then you adjust the variable resistor, and then take another reading. 10.17. Core practical. Construct electrical circuits to investigate the relationship between voltage, current and resistance for a resistor and a filament lamp, and test series and parallel circuits using resistors and filament lamps. So that's using Ohm's law. And as I've just explained for 10.16, would use this circuit and you would get the current and voltage reading for that particular device. So they're saying for a resistor and for a filament lamp. And then once you've got your current and your voltage readings, adjust the variable resistor and take your readings again, and do that a minimum of 6 times in order to get enough data to plot a graph. And here's the type of graphs that you'll end up getting. In 10.18, it's asking you about those graphs. So you've got to explain how current varies with potential difference for the following devices and how this relates to resistance. So for a filament lamp, a diode and a fixed resistor. So the IV graphs, the current voltage graph, current goes up the side, voltage goes along the bottom, and you'll notice I've done positive currents going down to 0 and then negative currents. So that's why we've got this crisscross graph here. I've got negative voltages on as well. Now this is for a bulb, or as I like to say, a spulb, because it looks like an S shape. Here is a diode, and here's the current voltage graph for a fixed resistor. Now, the flatter that the graph is, that means that resistance is increasing. So it starts off steep, so resistance is small for a bulb, and then the resistance increases. If they ask you why does it do that, you say because the bulb gets hot, and that's what increases the resistance. A diode has got a massive resistance in the reverse direction, so it doesn't matter how big the negative voltage gets, the current still remains 0. And in a forward direction, once the voltage gets to positive 0.6, then the current starts to flow. And it's a steady current, so it's a steady resistance, and it's quite a steep slope, so that means it's a smaller resistance. And for a fixed resistor, well, obviously the resistance is fixed. So you get a steady slope. Sometimes the slope can be steep, which means it is a small resistor, or sometimes the slope is flatter, which means that it's a bigger resistor. But it would still be a straight line to say that it's a fixed resistance. 10.19. Describe how the resistance of a light-dependent resistor, LDR, varies with light intensity. So if we plot light intensity along the bottom, going from dark to bright, and resistance up the side, when it's dark, the resistance is big, and as it gets brighter and brighter, the resistance decreases. Make sure you also note that the resistance decreases in a non-linear way. That's what you tell the examiner for your second mark. And that's the symbol for the LDR. 10.20. Describe how the resistance of a thermistor varies with change of temperature. So that's a negative temperature coefficient thermistors only. So negative temperature coefficient basically means as one thing gets bigger, another thing gets littler. In other words, as the temperature increases and it gets hotter, the resistance decreases. 1 mark for saying that, and 1 mark for saying it decreases in a non-linear way. So it's exactly the same shape for the thermistor as it was for the LDR. Explain how the design and use of circuits can be used to explore the variation of resistance in the following devices: filament lamps, diodes, thermistors, and LDRs. So basically it's similar to the core practical. We'd use that circuit there in order to get multiple readings and to plot these graphs here and these graphs here. Recall that when there is an electric current in a resistor, there is an energy transfer which heats the resistor. So basically, if you put current into a resistor, the resistor is going to get hot. That's all you need to know. Explain that electrical energy is dissipated as thermal energy in the surroundings when an electrical current does work against electrical resistance. In other words, you tell the examiner that resistors get hot when current passes through, and if it says where does the energy go to, you say to the surroundings for your third mark. Explain the energy transfer as a result of collisions between electrons and the ions in the lattice. So why is it that resistors get hot when current passes through? Well, if you were to think about it in terms of particles, the little electrons that make up the current that's trying to go through the wire collide into the ions that make up the wire, like the copper ions, you know? Now, every time there's a little collision between the electrons and the ions, there's a little bit of friction, and the friction causes heat. So that's why the resistors heat up. I've got a nice little video all to do with that. If you want to watch it, I'll put a link at the top of the screen. Explain ways of reducing unwanted energy transfer through low resistance wires. In other words, if you do not want your wires to get hot, so you want less heat, you'd better use low resistance wires. Now, a low resistance wire will be a short wire and a thick wire. The shorter it is and the thicker it is, the lower the resistance. Describe the advantages and disadvantages of the heating effect of an electric current. Well, the heating effect of current is an advantage, so it's good, if you want the device to get hot. So in other words, if you've got a heater or a hairdryer, you want that thing to heat up on purpose to create heat. Obviously, it's a disadvantage in any device not designed to get hot. So if you've got current making your device get hot and it's not supposed to get hot, such as in a phone or a PC, that basically means you could damage your components. You could damage your phone, you can damage your PC. Well, that's a big disadvantage of the heating effect of an electric current. 10.27. Use the equation energy equals IVT. I prefer to say energy equals ITV. So that is basically energy equals current I times by potential difference V times by time T. I say Emmerdale is on ITV, which is a TV channel in England. You make up your own one if you're not from England. And they'll basically give you values, you pop it in, and out pops the answer. 2 or 3 marks. Thank you very much. 10.28. Describe power as the energy transferred per second, and recall that it's measured in watts. So you might get 1 mark for saying power is energy transferred per second, and 1 mark for saying watts. Simple as that. Recall and use the equation. Power equals energy transferred divided by time taken. Make sure your time is in seconds. So P equals E over T. Remember that energy transferred equals work done. So you could say work done divided by time is also power. Remember, this year you're going to get given all the equations. 10.30. Explain how the power transfer in any circuit device is related to the potential difference across it and the current in it. In other words, power equals current times by voltage. They might also ask you to use power equals I squared times by R, just to show you where that comes from. If P equals I times by V, and also if V equals I times by R, if we take that V out and put I times by R in instead, so therefore it becomes P equals I times by R. Or we'll just simplify the I times by I as I squared. So P equals I squared times by R. And you'll just be expected to put the numbers in. Unit SP12, Magnetism and the Motor Effect. So you can see these are green, these statements here. So there's a good chance they'll be on the exam, but not much chance that these yellow ones will be, or just a little bit if they are. Recall that unlike magnetic poles attract, just like that, and like magnetic poles repel. So a north repels a north, a south repels a south, and a north and a south will attract. Describe the uses of permanent and temporary magnetic materials, including cobalt, steel, iron and nickel. Well, the first thing is, make sure you know that they are the 4 magnetic materials that you'll need to talk about at GCSE. And the uses, well, the uses of permanent magnets. For 1 mark, you use them in a fridge door, or for separating recycling, like steel cans from aluminium cans. And uses of temporary magnets could be maglev trains, which is magnetic levitation trains, and electromagnetic cranes found in junkyards and places like that, where they've got to move metal from one place to another. and they use temporary magnets. What they mean by that is electromagnets, so they can turn them on and off. Explain the difference between permanent and induced magnets. So a permanent magnet is always magnetic. Well, that's easy, isn't it? It's always got a magnetic field around it. But an induced magnet, they are only magnetic when in another magnet's magnetic field. So if you just had a piece of iron, it wouldn't have its own magnetic field. But if you put that piece of iron next to a magnet, it'll gain its own magnetic field from the permanent magnet. So the permanent magnet goes north-south. The induced magnet would also be north-south. So make sure you do the north next to the south. I've got videos on my YouTube channel in all these different playlists. If ever you need any extra help, check out the full videos. Describe the shape and direction of the magnetic field around bar magnets and for a uniform field, and relate the strength of the field to the concentration of the lines. Now that's what I've just explained with the electric fields. So with a bar magnet, you've got the lines are closest where the poles are. So the magnetic field is strong here because the lines are close together, exactly the same here. And the magnetic field is weak on the outer edges over there and over here, further from the magnet. And that's because the further away from the magnet you get, the weaker the magnetic field is. We represent the strength of the magnetic field by the lines. And the magnetic fields come out of the North Pole and go into the South Pole. Describe the shape and direction of the magnetic field around a bar magnet and for a uniform field. So for a uniform field, you'd have this plate here and this plate here, which are parallel to each other. And you'd have a uniform magnetic field lines equally spaced out, going from the north to the south. Notice around the edges here, it's not quite uniform, so it's just this part right in the middle between the two poles. Describe the use of plotting compasses to show the shape and direction of the field of a magnet and the Earth's magnetic field. So the field around a magnet, what you basically do is just put plotting compasses all over the place. You can see I've strategically placed them to show that the field comes out of the North Pole and goes into the south. So these compasses here would show the shape and direction of a magnetic field. And what you do is you just, whichever way the compass is pointing, draw a little arrow coming out of the compass on the paper next to it. Little arrows coming out like that. And then you just connect all those arrows together there, connect all these arrows together there, and just do the same coming down that way. I've got a video that shows you how to do it if you don't understand what I'm talking about. And the Earth, where the North Pole is and the South Pole is, there's exactly the same field coming out of the Earth. But obviously it's not horizontal like that. The poles would be vertical. Explain how the behaviour of a magnetic compass is related to evidence that the core of the Earth must be magnetic. Well, basically, a compass points to Earth's North Pole. That'll get you 2 marks. Describe how to show that a current can create a magnetic effect around a long straight conductor, describing the shape of the magnetic field produced and relating the direction of the magnetic field to the direction of the current. So you want to use the right hand grip rule for a straight wire. So point your thumb up, point your fingers round like that. Your thumb shows which direction the current's going as it's going through the wire. In this case, the current's going upwards. And the fingers would show which way the field goes. Now the magnetic field direction is from north to south, same as usual. Knuckles is north and fingertips is south. So if you pointed your thumb up, your fingers would come around in a circle like that. If you were looking down on it, it would be anti-clockwise. And the current is conventional current, which is from positive to negative. Now I'm probably telling you far too much detail because it's just yellow. Recall that the strength of the field depends on the size of the current and the distance from the long straight conductor. Yep. If you increase the size of the current, that'll make it a stronger magnetic field. And if you are closer to the wire, you'll have a stronger magnetic field. So a strong magnetic field next to the wire and a weak magnetic field as you move further away from the wire. You can see these lines here are close together, but these lines further apart are further apart. We always use the lines to represent the strength of magnetic and electric fields. Explain how inside a solenoid, so that's an example of an electromagnet, which is basically just a coil of wire. That's what a solenoid is. The fields from individual coils add together to form a very strong, almost uniform field along the center of the coil. That's that there. And they would cancel out to give a weaker field outside of the coil. All right. So the magnetic field from here interferes with the magnetic field out there, and you end up with a weaker field out here and a weaker field out there, and nice and strong in the middle. And you'll notice, yes, it's nearly uniform because these yellow lines that I've drawn for the magnetic field are nearly parallel to each other. Notice that the right hand grip rule for the solenoid is different to the right hand grip rule for a straight wire. The thumb this time doesn't represent the current, it represents the direction of the magnetic field, and the fingers this time represent the current, where the current's going. So the current's going from the front of the screen to the back of the screen, front of the screen to the back of the screen. Well, you can see these fingers are coming from the front down to the back. But it's only worth 1 mark, so you'll not need to know that. Recall that a current carrying conductor placed near a magnet experiences a force, and that an equal and opposite force acts on the magnet. Well, that would be the same as placing 2 magnets together. So if you placed a magnet inside this magnetic field, it's going to repel or attract. Explain that magnetic forces are due to interactions between magnetic fields. Yeah, that's just a statement. Recall and use Fleming's left-hand rule to represent the relative directions of the force, the current, and the magnetic field for cases where they are mutually perpendicular, which means all at 90 degrees. So Fleming's left-hand rule is this here. Your thumb represents the movement, first finger represents the magnetic field, second finger represents the current. I've got a nice video on that if you want to know more, but you don't really need to know more because it's yellow. Use the equation F equals Bill. So that's the force on a conductor at right angles will equal the magnetic flux density times by the current times by the length. So if it is on your exam, they'll just give you the equation and the numbers and just pop them in. Unit SP13, Electromagnetic Induction. So you can see the foundation candidates don't need to know any of this. The higher candidates only need to know this. 13.2. Recall the factors that affect the size and direction of an induced potential difference and describe how the magnetic field produced opposes the original charge. I think that's supposed to say original change. So to get the size and direction of the induced potential difference or induced voltage, well, the size of the voltage gets bigger if you have a faster movement of a magnet. So remember, you are moving a magnet in and out of a coil. If you have a faster movement, you'll get a bigger voltage. If you use a stronger magnet, you'll get a bigger voltage. If you use more coils, you'll get a bigger voltage. So it's just common sense, really. And the direction of the voltage reverses if the magnet's reversed. So if you put a magnet in, you might get a positive voltage, in which case if you pull it back out, you'll get a negative voltage. The direction of the voltage reverses if the magnet is reversed. So, for example, if you push the north pole of a magnet into a coil, let's say you get a positive voltage. That means if you push a south pole in, you'll get a negative voltage. Another way to reverse the direction of the voltage is by reversing the direction of the movement of the magnet. So if you push a north pole in and you get a positive voltage, that means when you pull a north pole out, you'd get a negative voltage. So if you reverse the movement, you reverse the voltage. 13.5. Explain how an alternating current in one circuit can induce a current in another circuit in a transformer. Right, so what you basically tell the examiner, this is a transformer. You've got a primary coil and it's not actually connected electronically to the secondary coil. What it is it's connected via an iron core. Now what you do is you put an alternating current in to the primary coil. 1 mark for saying that. Make sure you say AC and not DC. Now that will create an alternating magnetic field in the iron core, and then the alternating magnetic field in the iron core creates an alternating current in the secondary coil. So you could get 1 mark for that, 1 mark for that, and 1 mark for that. But of course it looks like you mightn't even need to know that, or it mightn't come up on your exam, or if it does, it's only worth 1 mark, 1 or 2 marks. Recall that a transformer can change the size of an alternating voltage. So once again, it's letting you know transformers only work with alternating voltage or alternating current. Now the 2 types of transformers you'll get, and again, probably don't need to know too much detail here, is the step-up transformer, which steps up the voltage, in other words, makes a small voltage into a big voltage, and a step-down transformer, which steps down the voltage. So whatever it says it does is what it does to the voltage. So in other words, if you put a big voltage in, it'll step it down and you'll get a small voltage out. A step-up transformer has less turns on the primary coil and more turns on the secondary coil. In other words, the number of coils step up, and that's why it's called a step-up transformer. Step-down transformer, you get more turns on the primary coil and less turns on the secondary coil. But for 1 mark, I've probably told you too much detail there. Unit SP14, Particle Model. This is probably going to be on the exam. This will be on the exam. These probably won't, or if they are, just 1 mark. Use a simple kinetic theory model to explain the different states of matter. So remember, that's solids, liquids and gases, in terms of the movement and arrangement of particles. So here's your 3 states of matter: solid, liquid and gas. Now your particle arrangement, you say that the solid is in nice neat rows, you get fixed volume, fixed shape, and the particles are very close together. As a result, the density will be very high. And how do the particles move? Well, by vibration only, because they're bonded together. The particles in a liquid are irregular, which means they're all over the place. They've still got a fixed volume, but they don't have a fixed shape. They'll fill the shape of the container. And the particles are close together as opposed to very close in the solids. How do they move? Well, the particles move slow and randomly. Particles in a gas are irregular, so it means they're all over the place. Not a fixed volume this time. A gas will fill the volume of the room. It's not a fixed shape either, and the particles are far apart. How do the particles move? Rapid and random. Or if you don't like the word rapid, just say fast and random. Recall and use the equation. Density equals mass divided by volume. So we use a wiggly P for density, M for mass, V for volume. Core practical. Investigate the densities of solids and liquids. Now this is going to be one of the core practicals, so it's worth 6 marks. So let's have a good look at this. So if you're going to investigate the density of a regular solid, for example a cube, well, always base your explanation on the calculation. So to get the density of whatever, you need to know the mass and the volume. Tell the examiner you'll use this equation. Tell the examiner that to get the mass, you'll use a mass top pan balance. And to get the volume, because it's a regular shape, you just do the height times by the width times by the depth. So just use a ruler. In order to get the density of an irregular solid, so that means like an odd shaped solid, again, tell the examiner you're going to use density equals mass over volume. Now you can get the mass once again just by using a mass top pan balance, so it doesn't matter that it's a funny shape, you can still put it on the top and you'll get the mass. However, this time to get the volume, what you'll need to do is take a measuring cylinder, so tell the examiner that, and fill it up with water to say halfway, and then plop the shape into the water and the water will rise. Now if we say the volume at first was volume 1 and the volume after you've put the object in is volume 2, then to get the volume of the irregular shaped solid, just do volume 2 take away volume 1. And that will also get you anything up to 6 marks. Now if you're going to get the density of a liquid, well, get a measuring cylinder, put it on top of the mass top pan balance, and then press the tare button to take it back to 0. When you put your liquid into the measuring cylinder, the mass top pan balance will just tell you how much mass of liquid there is. And the beauty of this is at the same time, the measuring cylinder will also tell you the volume. So you just get the mass and the volume by using a mass top pan balance using that technique. Explain the differences in density between the different states of matter in terms of the arrangements of the atoms or molecules. So specifically to do with the density, solids, the density is very high, liquid density is high, and gas density is low. So with the exception of water and ice, most solids are more dense than their liquid variant. And as they turn into a gas, so that's another physical change, generally the particles spread out even more. Describe that when substances melt, freeze, evaporate, boil, condense or sublimate, mass is conserved. So that just means the mass that goes in equals the mass that comes out. And that these physical changes differ from some chemical changes because the material recovers its original properties if the change is reversed. So sometimes if you have a chemical change, the properties will be totally different and you can't reverse it. But if you're just changing the state of matter, that's just a physical change. And if you reverse the change, you'll get the same properties back. So if we start with solid, go into a liquid, go into a gas. A solid melts and turns into a liquid, and then it evaporates or boils and turns into a gas. If you cool the gas, it'll condense to form a liquid. Once you've got the liquid and you cool it, it'll freeze to a solid. When it's a solid, it doesn't have much energy. When it's a liquid, it's got more energy. And when it's a gas, it's got high energy. And sublimate is when you turn from a solid directly into a gas without going into the liquid state of matter. Explain how heat in a system will change the energy stored within the system and raise its temperature or produce changes of state. So that's what I've just said there. The solid has got a low amount of energy, a liquid's got medium amount of energy, gas has got a high amount of energy. You know, you could be asked that in your exam, you get 1 mark for each of those things. Define the terms specific heat capacity and specific latent heat and explain the difference between them. So remember, it's only worth 1 mark. Well, specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree C. Specific latent heat, for 1 mark in an exam, it's the amount of energy needed to change 1 kilogram of a substance from one state to another without changing its temperature. In other words, specific latent heat is what you use if there's a change of state. Specific heat capacity is what you use as you're heating one state and it's getting close to either the melting point or the boiling point. Use the equation. Change in thermal energy Q equals the mass times by specific heat capacity times by the change in temperature. Now, you'll have to rearrange that sometimes in order to find the specific heat capacity. So if you know how much energy you're putting into a liquid or a solid, and you know the mass of the liquid or solid and how much it's changed its temperature by, then you'll be able to work out what the specific heat capacity of the solid or the liquid is. Use the equation Q equals M times by L. So that's the amount of thermal energy needed for a change of state. And that's the mass times by the specific latent heat. Explain ways of reducing unwanted energy transfer through thermal insulation. In other words, wrap up something in foam or put a lid on it if you don't want to waste thermal energy from that thing. 1 mark for each of those things. Now here we go, here's the 6 marker, this is your core practical. So this will definitely be on the exam. Investigate the properties of water by determining the specific heat capacity of water and obtaining a temperature time graph for melting ice. So here's how to determine the specific heat capacity of water. You'd need to fill a container with a known mass of water. And for another mark, measure the starting temperature of the water. For your 3rd mark, use a heater connected to a joule meter to heat the water. Measure the final temperature of the water. Measure the amount of heat energy used. And then calculate the specific heat capacity by using C equals Q divided by mass times by temperature change. The temperature change will be the final temperature. Take away the temperature at the start. I've got a nice little video all to do with that. Definitely recommend you watch it. Obtaining a temperature time graph for melting ice. Right, what you do is you tell the examiner that you would heat some crushed ice. You'd record the temperature and the time. So say heated for 10 minutes, record the temperature over the 10 minutes. And then use those results to plot your temperature time graph. Now what you should find is when it's ice, it'll start to heat up and heat up. Now once it changes from ice, which is a solid, into water, which is a liquid, during the melting process, you should end up with a flat part of the graph. It's what we call a plateau, and that's because it's changing state. Now you're still putting energy in because you're still heating it. So you say, well, where's that energy gone? Because the temperature's not going up. The energy is being used to break bonds, turning it from a solid into a liquid. Once it's fully turned into a liquid, then the temperature will continue to go up. Once it reaches a change of state again and changes from a liquid into a gas, once again you'll end up getting a flat part, which is your plateau. Now these plateaus, because there's no change in temperature, that's when you'd use this equation here. Q equals M times by L. You'll notice there's not a change of temperature involved when you're using the specific latent heat as it's changing state. As it's changing the temperature and this section here and this section here, that's when you would use the equation for specific heat capacity, which does involve the change of temperature in the calculation. Again, if you're not sure about that, check out my video from the SP14 playlist. Explain the pressure of a gas in terms of its motion of its particles. You just need to say that the pressure of the gas is because of the motion of the particles. Pressure is caused by collision of particles. For 1 mark. Explain the effect of changing the temperature of a gas on the velocity of its particles and hence the pressure. Well, if you increase the temperature, that's going to increase the velocity of the particles and that's going to increase the pressure. And it does say for a fixed mass of gas at a constant volume. Describe the term absolute zero minus 273 degrees C in terms of the lack of movement of particles. So just make sure you know that the coldest temperature you can ever get is called absolute zero, and it's at minus 273 degrees C. And at that point, there's no movement of the particles, or it's very, very minimal. And therefore, if the velocity is zero of the particles, then there'll be no pressure either. It's only worth 1 mark though. Convert between Kelvin and Celsius scales. So if it does ask you to do this, to convert degrees Celsius into kelvins, take the degrees Celsius and add 273 to it. For example, if you've got 27 degrees C, that'll actually be 300 Kelvin. And to go from kelvins into degrees Cs, you take 273 away. So if you had 300 Kelvin, that's actually just 27 degrees C. Unit SP15, Forces and Matter. Neither the foundation nor the higher candidates need to know anything from this unit. So that's the end of the video. So I hope that helped you. Remember, I've got 24 years of experience. I've seen lots of exam papers, teaching physics for 24 years. And the way that I've explained each of the specification references is trying to keep it as simple as I can, and you tell the examiners what I've said and you should be able to pick up a lot of marks. So work hard, be nice, and bye for now.